So today we get to the last chapter we're going to cover in this summer session, and it's chapter 30. We're not going to get to all of chapter 30. We're going to talk about inductance in a inductance in a circuit. We're only going to focus on the role of inductance in direct current circuits. We're not going to get into the role of inductance in AC circuits, which is actually very important, but that's a subject for Physics 3. So you're going to have to wait for that, unfortunately. But what is inductance? Well, it applies directly to what we covered in the last chapter, which is Faraday's law of induction. That a changing magnetic flux within a coil of wire will create a potential difference within the coil of wire that acts to oppose the change. Well, you can have a circuit where you have this coil of wire and you turn the power on, the current builds up from 0 to whatever value it's going to get, but as it's building up, so as the current going through the coil of wire builds up, the magnetic flux through the coil of wire is also building up, which means you're going to have an induced EMF in the opposite direction of the current. So you're going to have an opposition to the increase. And so there are some consequences of that. One is that it's possible to store energy in an inductor, and we'll talk about that in a little bit. Two, that it takes time to build up from 0 to the maximum value. And so how does the EMF look? So we're going to define the EMF going through what's called an inductor as being equal to the inductance of the inductor, which is defined as capital L, multiplied by the change in current with respect to time. So L is called the self-inductance of the circuit, and it's measured in units of henries. So if your EMF is in volts, your current is in amperes, and your time is in seconds, your the inductance is going to be in henries. And comparing the equation I just showed you with the EMF is equal to L times di over dt, comparing that to Faraday's law of induction, you get the self-inductance is equal to capital N, which is the total number of turns in the coil, times the derivative of the magnetic flux with respect to the current. So that comes from the chain rule. In nearly every application, and certainly in every application we're going to be dealing with in an introductory level physics class, the magnetic flux is directly proportional to the current, that it varies linearly with the current. And so you can write that relationship as being equal to capital N times the magnetic flux divided by I. So if the magnetic flux varies linearly with I, the I terms will ultimately cancel out, and the inductance will only depend on the geometry of the coil, of the dimensions of the coil, and the total number of turns in the coil. So for most circuits, the inductance is small unless you have a coil of wire called an inductor put in to specifically increase the inductance of a circuit. So the key to creating inductance in a circuit is to have a coil of wire with many turns. So capital N is the number of turns in the coil. So the most obvious example of an inductor is a solenoid. So again, L is equal to N times the magnetic flux divided by I. So the magnetic flux of a solenoid is equal to the magnetic field. And remember, the solenoid is a cylindrical coil with capital N turns of length L and radius R. So the magnetic field is mu naught times capital N over L times I. That's the magnetic field inside a solenoid. And you're multiplying that by the area inside, or the cross-sectional area of the solenoid, which is pi r squared. And you're dividing that by I. And so what you get out is that L is equal to mu naught, the permeability of free space, times n squared, So it depends on the square of the total number of turns in the coil of wire divided by the length of the solenoid, so the length of the cylinder, and multiplied by pi r squared. So it depends on the total number of turns and the dimensions of the cylinder. Now, you can magnify the self-inductance of a coil of wire by placing a piece of iron or something else that exhibits what are called ferromagnetic properties inside the solenoid. So again, getting back to what we've talked about a couple of times already, that iron, when it has electrons rotating in circles that basically have their own magnetic dipole moments, and if you expose them to an external magnetic field, those dipole moments will align themselves so that they point in the same direction as the magnetic field. And what that serves to do is strengthen very greatly the magnetic field that's inside. And one of the consequences of that is that you can strengthen the self-inductance of a coil quite a bit by including a piece of iron. So with a piece of iron, L is equal to a proportionality constant times mu naught n squared over script L, the length of the cylinder, times pi r squared. But you can write that constant times mu naught as simply mu. So the you can think of that as the permeability of iron or whatever other material you're looking at. And it's basically a number, a multiplying factor times mu naught. And everything else is otherwise the same. So with that, let's go to some examples. If the current in a 280 millihenry coil changes steadily from 25.0 amps to 10.0 amps in 360 milliseconds, what is the magnitude of the induced EMF? So this is a basic application of the general equation for the voltage across an inductor. So delta V is equal to, and we use the magnitude of it, and so the magnitude of delta V is equal to the inductance times the magnitude of the change in the current with respect to time. And remember, the direction of the induced voltage is such to oppose whatever change in the magnetic flux caused it. So we have the inductance L. It's a 280 millihenry coil, and millihenries are a typical unit for inductors. 1 Henry inductor is a pretty large inductor, at least if there is no iron inside, it's a pretty large inductor. So in regular SI units, that's 0.280 henries. And again, we want to put it in regular SI units so that the answer you get is in volts. So it's 0.280 henries. And then you want the change in the current with respect to time. And so it's a steady change. So it's negative 15 amps because it's decreasing by 15 amperes. And the denominator, so this all takes place in 360 milliseconds. So again, convert milliseconds to seconds. You divide by 1,000, that's 0.360 seconds. And we put the absolute value signs in so that we get, just the magnitude of the induced EMF. And so we get to 3 significant figures, 11.7 volts. So that's the magnitude of the induced EMF. So now we're going to go to another example. So let's show this real quick. How many turns of wire would be required to make a 130 millihenry inductance out of a 30.0 centimeter long air-filled coil? So you're not putting anything special inside. It's just a hollow cylinder with a diameter, again, it's a diameter, not the radius, be careful of that, of 4.2 centimeters. So let's set this up. So again, inductance depends on the dimensions. So L, capital L, is equal to mu naught capital N squared over script L times pi r squared. So notice you're multiplying by pi. You're not, the pi terms are not going to cancel out in this case. So be mindful of that. The easiest thing to do would be to multiply pi squared by 4 times 10 to the negative 7. But ultimately here, we want to find n. We're asked for how many turns of wire. And everything else we are given. So let's set this up in terms of n. So we multiply both sides by L. So we have capital L times script L. And then in the denominator, that's mu naught pi r squared. So you divide both sides by mu naught pi r squared. And here you notice it's n squared, not simply n. So you're going to need to take the square root to get the total number of turns in the coil. So let's plug the values in and see what we get. So the inductance is 130 millihenries. So again, keep everything in SI units, 0.130 henries. The length is 30.0 centimeters. So that's the length of the cylinder. And in SI units, that's 0.300 meters. And then that's mu naught, which is 4 pi times 10 to the negative 7 Tesla meters per ampere with another pi term. So what you're going to do is you multiply these two numbers together, then divide by pi squared, then divide by 4 times 10 to the negative 7. And don't forget, you need the radius, but you're given the diameter. The diameter is 4.2 centimeters. The radius is going to be half that, which is 2.1 centimeters, or rather 0.021 meters. And don't forget you're squaring that. So that's all the information you need. So you start plugging the numbers in. So it's 0.13 times 0.300 divided by, and again here divide by pi squared, and then divide by 4 times 10 to the negative 7, and then divide by 0.021, again that's the radius in meters squared, and you get a pretty large number, but don't forget you're taking the square root of that. And so to two significant figures, because this value is only two significant figures, that's 4.7 times 10 to the 3. So about 4,700 turns in the coil over the course of 30 centimeters. So 30 centimeters is about a foot. And so, you know, it's a pretty tightly wound wire, but if you want to get a noticeable inductance, that's what you have to do. Okay, so now moving back. Now we're going to talk about mutual inductance. So an inductor can induce an EMF in itself if the flux going through it is changing, but a coil of wire can influence a nearby coil of wire. And we kind of saw that with transformers, for example, that you have one coil of wire influencing the other coil of wire. And so that is called mutual inductance. That, I mean, if one, you know, if coil 1 can influence coil 2, then it works the other way, and coil 2 can exert an influence on coil 1. So we have two coils of current I1 and I2, and they have N1 and N2 turns. And they are near enough to each other that their respective magnetic fields influence each other. So basically, they can exert an influence on each other, and they can, a change in current through one can induce a current through the other. And that's basically what mutual inductance is. And if it works one way, it can work the other way as well. And possibly, they can work on each other simultaneously. So we're going to define psi12 as being the magnetic flux in coil 2 due to the current in coil 1. So the first number is the influencer, and the second number is what's being influenced. So psi12, the magnetic flux that coil 1 creates in coil 2. And psi21 is the magnetic flux that coil 2 creates in coil 1. So there are a couple of ways of thinking about that. And so that brings us to the definition of mutual inductance. And notice there's a symmetry. There are two equivalent ways to write this. And so the mutual inductance can be the total number of turns in coil 2 times the magnetic flux due to coil 1 in coil 2 divided by the current in coil 1. You can also write that as the total number of turns in coil 1 multiplied by the magnetic flux that coil 2 creates in coil 1 divided by the current in coil 2. Either way, you should get the same result. And conceptually, that's the most important thing to get out of this. That either way, you're going to get the same result. That if you work one way, you'll get a certain result, and if you work the other way, you should get the exact same result. And it's a good check on your work that if you do it both ways and you get the same results and you understand why you get the same results, then you can be pretty confident that you've got the right answer. So the induced voltages across the inductors are given as follows. So delta V1, the induced voltage in the first coil, is equal to negative M times di2 over dt. So again, the induced voltage is such to oppose the change of the current in I2. And delta V2 is negative M times di1 over dt. So it opposes the change of the current in I1. So if the current in I2 is clockwise and increasing, then the I1 is going, or the delta V1 is going to be counterclockwise. And so it works like that. You're opposing the change. So let's do another example. A 2.44 meter long coil. So we have a very long cylinder is containing 225 loops, which is actually not that many loops for that length of cylinder. And it's wound on an iron core. So the average mu is equal to 1,815 times mu naught. So again, you put iron inside a coil of wire, you're greatly strengthening the whatever magnetic field influences it. You're magnifying whatever magnetic field. In here, you're going to magnify the magnetic field by nearly 2,000, or by a factor of nearly 2,000. And you are going to magnify the inductance by that magnitude, 1,815. And then there's a second coil of 115 loops wrapped around the same iron core. The loops of each coil have a radius of 2.00 centimeters. So we know the geometry of the coil. We know its length, and we know the geometry of the cylindrical coil. We know its length, and we know its radius. If the current in the first coil drops uniformly from 12.0 amperes to 0 in 98.0 milliseconds, determine the mutual inductance M and the EMF induced in the second coil. So the mutual inductance M, we'll start with that. So we'll define the first coil as our, we'll say delta I1 is negative 12.0 amperes. So we want to find the mutual inductance and then the EMF induced in the second coil. So we're asked to find M and delta V2. So we know what variables we're finding. Now the mutual inductance, again, you can do it a couple of ways, but the mutual inductance is equal to, and we'll do it as N2 times phy230 divided by I1. And that's a comma. So that's N2 times phy230 divided by I1. So N2 is given. Phi is the magnetic flux due to current 1 on, or due to coil 1 on coil 2. So the magnetic flux, again, mutual inductance problems can actually get pretty complicated. So we're only going to look at some simple situations where it's easy to figure out. So here, they're wrapped around the same coil. So the magnetic flux due to the, in the first coil, or due to the first coil, is mu, not mu naught, because we have iron inside, times N1 over L, times I1, and that's script L, times pi r squared. And you're dividing that by I1. So the I1 terms cancel out, and you're left with mu, N1, N2. Again, the N2 is just the beginning. The N1 comes in because you're looking at the flux caused by coil 1 on coil 2. And so you have mu times N1, N2 over script L times pi r squared. And you can see from the symmetry, it's going to be the same working in the other direction. And so you could go the other way and you would get the exact same answer, and you should get the exact same answer. So that's the mutual inductance. And so now we want to calculate, and the mutual inductance, just like self-inductance, is going to be in units of henries. So mu is equal to 1,815 times mu naught. So that's 1,815 times 4 pi times 10 to the negative 7 Tesla meters per ampere. And again, the pi terms will multiply together, not cancel each other out. You want the number of turns around the coil, so that's 225 and 115. And you're dividing by the length of the cylinder, which is 2.44 meters. So it's a very long cylinder. And then you're multiplying by pi, and then the radius is 2.00 centimeters, and here they do give the radius. So you don't need to divide this by 2. That's just 1.00 centimeters, or 0.0, or rather, you don't need to divide it by 2. So that's 2.00 or 0.200 meters. And again, you're squaring that. So again, the easiest way to tackle the pi's is to multiply them together. So you have 1,815, multiply that by pi squared. That way you get rid of the pi's, and then multiply by 4 times 10 to the 7. So you have those, and then you're multiplying by 225. and then by 115, dividing by 2.44, and then multiplying by 0.02 squared. And what you get is you have three significant figures. So you get 0.0304 henries. And you can also, if you prefer, write that as 30.4 millihenries. So that's the mutual inductance between those two wires wrapped around the same coil. You're actually going to have a lab experiment when we talk about Faraday's law, where you were going to wrap a coil of wire around a solenoid. And so you're going to look at what is happening through that. And but we're not going to talk about mutual inductance directly there. We're going to basically quantify Faraday's law of induction using that. So that's M. And so the last thing you want is delta V2. So delta V2 is equal to negative M times di1 dt. And so that's negative M. And so it's multiplied by, or we know what M is. So it's negative 0.304 henries. Multiplied by di1, so that's negative 12.0 amperes. And you're dividing by the time, and so that's 9.80 milliseconds. So in seconds, that's 0.0980 seconds. And so you get the voltage out of that. Now notice the negatives cancel each other out. So and when you plug this in, you get 3.72 volts, and it's positive 3.72 volts. So what's the significance of the sign here? Well, what you have is that I1, it could be going clockwise from your vantage point or counterclockwise, but the point is it's decreasing. So the induced voltage in I2, or the induced voltage in coil 2 is going to oppose that decrease. So the current then in coil 2 is going to circle around the coil in the same direction that the decreasing current in I1 is going. So it's going to oppose the decrease. And opposing the decrease means it's going in the same direction. Okay, so that's mutual inductance. Now, there are two important consequences of inductance. One is that you wind up storing energy in an inductor. And in fact, you wind up storing quite a bit of energy in an inductor. You can store more energy in an inductor than you can in a capacitor, given typical values of the magnetic field and the electric field. And so we'll talk about that in a couple of minutes. But because of the opposition to reaching maximum current that self-inductance creates, you have to do work to overcome that opposition. And so that work adds stored energy or potential energy to the circuit, and the potential energy is equal to 1/2 times the inductance times the square of the current. So if you double the current, you're quadrupling the amount of energy that you're storing in the circuit. Now we're going to talk about how much energy is stored per volume. So you think of an inductor as a cylinder, and you think of your typical solenoid, it's a cylinder. So how does that work? Well, we know what the inductance of a cylinder is. It's mu naught times n squared over script L times A, the cross-sectional area. And B, the magnetic field inside the solenoid or inside the inductor is mu naught times n over script L times I. So you plug those in, And what you get is U is equal to 1/2 times Li squared, which is equal to 1/2 times mu naught times N squared over L times A. And then solving the magnetic field equation for I, you wind up multiplying by the square of B times script L divided by mu naught N. And so you plug all those terms together. Notice the N's drop out. You're left with B squared times script L times A divided by 2 over mu naught. But script L times A is just the volume of the solenoid, the volume inside, inside your coil of wire. So you can write the energy density small u, that's U divided by the volume, as being equal to B squared over 2 divided by mu naught. So a given magnetic field through a coil of wire stores an amount of energy per unit volume equal to the square of the magnetic field divided by 2 times mu naught. So that's the energy, if you keep B in Tesla and mu naught in Tesla meters per ampere, you will actually get an energy density in joules per cubic meter. So we're going to go through a couple of examples here. So the magnetic field inside an air-filled solenoid, 38.0 centimeters long and 2.10 centimeters in diameter, is 0.600 Tesla. Approximately how much energy is stored in this field? So again, there are a couple of ways you could do this, given the information that you have. But the total energy is equal to small u times the volume. And you realize there's the potential for confusion there. Actually, that won't make it any less confusing. So be careful not to confuse volume with voltage in this. So that's U, or small u, is B squared over 2 mu naught times the volume, which is script L, the length of the cylinder, multiplied by pi r squared, the cross-sectional area of the cylinder. So these are all things that we more or less have. So the magnetic field is 0.600 Tesla. So we have 0.600 Tesla, and you're squaring it, divided by 2 times 4 pi times 10 to the negative 7 Tesla meters per ampere. And here the pi's do cancel out. But that's L. The length is 38 centimeters, or 38.0 centimeters long. So in SI units, that's 0.380 meters. And so you divide the 38 by 100. And then that's pi. But the good news is the pi terms cancel out. And then the radius, and once again, we're given the diameter, not the radius. So the radius is the diameter is 2.10 centimeters. The radius is 1.05 centimeters. So we can write that as 1.05 times 10 to the negative 2 meters. And you're squaring that. And so you plug all those numbers in. So that's 0.6 squared divided by 2. And again, the pi terms cancel out. So you can just divide by 4 times 10 to the negative 7. Then multiply by 0.38. Then multiply by 1.05 times 10 to the negative 2 and square that. And what you get is 3 significant figures, so 9.43 joules per cubic meter. So that's a noticeable amount of energy. And this problem will show, this next example will show how to compare that to what you can store in an electric field. So let's look at this example. This example is problem number 16. Typical large values for electric and magnetic fields attained in laboratories are about 1.0 times 10 to the 4 volts per meter and 2.0 Tesla. Determine the energy density for each field and compare. So assume a parallel plate capacitor for the electric field. So you're storing energy in a capacitor and you're storing energy in a solenoid. So how does this look? Well, the first thing we're going to need to do is figure out energy density in a capacitor. And write it in terms of the electric field. So the energy stored in a capacitor is, and that's U, that's not E. So an electric. We are going to use, and there are 3 equations you could use. We are going to use 1/2 times C times delta V squared, because we don't know anything about the charge involved. But the capacitance depends on the dimensions, and the potential difference can be related to the electric field. Remember, E is equal to negative delta V over delta X. If the electric field is constant, you're going to get that relationship. And so delta V squared is equal to E squared, and we're assuming a parallel plate so that the space between the plates is the distance D. So we can write this as 1/2. For a parallel plate capacitor, that's epsilon naught A over D times delta V squared, which is E squared times D squared. So we can simplify this a little bit. That becomes 1/2 epsilon naught E squared. And then one of the D's cancels, and so you're left with the area of the plates multiplied by the distance between them. But that's just the volume enclosed by the parallel plate capacitor. So the volume inside the parallel plate capacitor. So again, we can write small u, and we'll make that small u sub E is equal to 1/2 times epsilon naught times capital E squared, where that's the strength of the electric field. So we're asked to figure out the energy density for each field and compare. Well, okay, we now have enough information to do that. So that's 1/2 times epsilon naught, and epsilon naught is 8.85 times 10 to the negative 12 coulombs squared per Newton meter squared. And you're multiplying that by E, and we're told E is 1.0 times 10 to the 4 meters. Or volts per meter, excuse me. And you're squaring that. So you plug those numbers in. So that's 0.5 times 8.85 times 10 to the negative 12 times 1 times 10 to the 4 squared. And you get 4 and this is two significant figures. So 4.4 times 10 to the negative 4 joules per cubic meter. So that's how much energy is stored per volume in a capacitor, and per volume of space inside the capacitor. That's how much energy gets stored. Now we're going to look at the magnetic field. So that's B squared over 2 mu naught. So a 2.0 Tesla magnetic field. Let me just double check that that's the right number. Yes, 2.0 Tesla magnetic field divided by 2 times 4 pi times 10 to the negative 7 Tesla meters per ampere. And again, you plug these numbers together, you're going to get a value in joules per cubic meter, but notice how much different it is. So 2 squared divided by 2 divided by pi divided by 4 times 10 to the negative 7 gives us, and we will all right, let's try that again. Okay. That's 1.6 times 10 to the 6 joules per cubic meter. That's a huge difference. That's 10 orders of magnitude. So you can actually store quite a bit more energy in an inductor than you can in a capacitor, given the same amount of space to work with. And it's really not close as far as how that works. So that's an important thing to keep in mind. Certainly if you're an EE major and you're looking for a practical point, you're looking at this from a practical aspect. If your goal is to store energy, you want an inductor rather than a capacitor. So part B, what magnitude electric field would be needed to produce the same energy as the 2.0 Tesla magnetic field? So we're given the energy, we're given 1.6 times 10 to the 6 joules per meter, and that's equal to 1/2 epsilon naught E squared. So we want, so we're going to use this equation, and we're running a bit low on space, but UE is equal to 1/2 epsilon naught E squared. And we want to solve this for E now using this, this value for the energy density, and to see how strong an electric field will give you that energy density. So E is, you multiply the energy density by 2 and divide by epsilon naught, and then take the square root. Just doing the algebra. So you multiply both sides by 2, divide both sides by epsilon naught, and then you take the square root, and that'll give you the magnitude of the electric field. So let's figure all this out. So that's 2 times 1.6 times 10 to the 6 joules per cubic meter. And you're dividing that by the permittivity of free space, which is 8.85 times 10 to the negative 12 coulombs squared per Newton meter squared. So let's plug that big mess in. And you take the square root, you get 6.0 times 10 to the 8 volts per meter. And you may be very hard pressed to find a capacitor. Certainly an air-filled capacitor won't cut it as far as that magnitude of electric field. That's, you get that strong of an electric field, the electrons will just jump right over and you'll lose the capacitor at that point. Okay then, so what that's telling you is that an inductor can store a lot more energy per unit of volume than a capacitor can. And so that's something, like I said, if you're doing practical design, that's something to keep in mind, that for a given amount of space, you can store a lot more energy using an inductor instead of a capacitor, assuming that you can generate, the laboratory, a 2 Tesla magnetic field or a 10,000 volt per meter electric field. So now we're going to get to RL circuits. And so this is very, very similar to RC circuits. So you have an inductor in series with a resistor, and you're measuring the amount of time it takes for the current to get to its maximum value. And so the voltage feeding into that portion of the circuit, whether it's the whole circuit or just a segment of it, is the voltage across the resistor plus the voltage across the inductor. So that's equal to IR plus L times di over dt. So you notice you get a differential equation in terms of I that's very, very similar looking to the differential equation in terms of Q that we got for the charge in a capacitor. What's different is the time constant. The time constant here is L divided by R. So you're not multiplying the resistance by the capacitance, you're dividing the inductance by the resistance. And so that's how you get the time constant. And your time constant is still measured in seconds. And so that I is equal to delta V when you go through the differential equation. And I won't repeat it, just go back to your notes or the video for the RC circuit and just follow along with the slightly different terms, but you get a very similar result, that I as a function of time is equal to delta V over R, which is the maximum current, and which is the current you would have if the inductor wasn't there, multiplied by 1 minus e to the negative t over tau. Keep in mind from this, inductances tend to be less than 1 Henry, and resistors tend to be quite a bit more than 1 ohm. So in a typical RL circuit, you've got a pretty small time constant. Usually you need to refer to the oscilloscope if you want to see the process of current building up, as a function of time. It's not something that's easy to observe in real time, unless you've got a piece of iron that you can stick inside the conductor. So now let's do an example, and then we're going to be done for this chapter. So after how many time constants does the current in figure 30.6 reach within 5.0%, 1.0%, and 0.10% of its maximum value? So let's visualize this. So we'll clear all this out. So you have your power supply, you have your resistor, and you have your inductor. And so the inductor is usually symbolized by a coil. And so the current is turned on, or rather the power is turned on, so the current builds up, but because there's an inductor, there's opposition. And so the current doesn't go to its maximum value right away, it takes time. And so I is equal to I max, which is delta V over R, times 1 minus e to the negative t over tau. And so not knowing what L and R are, you can just go with tau. And so we'll answer these questions, A, B, and C, as a function of tau. So after how many time constants? So basically your answer is going to be expressed as a multiple of tau. But so we're solving t, and it's going to be a number times tau. So let's set all this up. So the first thing we're going to do is divide both sides by the maximum value. So I over I max is equal to 1 minus e to the negative t over tau. And then what we're going to do is add the e to the negative t over tau to both sides and subtract I over I max to both sides. So you get e to the negative t over tau is equal to 1 minus I over I max. So 1 minus I over I max. Now, keep in mind what the problem is asking you. It's asking, so within 5% of its maximum value. So that's equivalent to saying, how long does it take to get to 95% of its maximum value? But when you write it like this, so 1 minus I over I max, you want to find what t is when 1 minus I over I max is equal to 5.0%, or 0.050. And so, you know, when you're within 5% of the maximum value. So when you're at the maximum value, the whole term on the right side of the equation is 0. But, so for part A, 1 minus I over I max is equal to 5.0%. So you want to get within 5% of the maximum value. So basically you want to get to 95% of the maximum value. And you can write that as 0.050. And then you go through the math. So you finish the steps from there. Negative t over tau is equal to the natural log of 1 minus I over I max. And then you can solve it. So t is equal to negative tau times the natural log of 1 minus I over I max, which is equal to negative tau times the natural log of 0.050. Now, the natural log of any number between 0 and 1 is going to be negative, so the negatives are going to cancel out. So you're going to get a positive number times tau, and that will tell you how many time constants it takes to get within 5% of the maximum value. And so to 2 significant figures, that is 3.0 times tau. So it takes 3 time constants to get within 5% of the maximum value. That's also true for charging up a capacitor. It'll take 3 time constants, so whatever your resistance and capacitor are, it'll take 3 time constants to get 95% charged, or to get within 5% of the maximum value. So then for part B, t is equal to negative tau times the natural log, and this is within 1%, I believe. Yes, 1.0%. So that's 0.010. And so that's what you put in. And you get 4.6 times tau. So if your time constant is equal to 1 second, it will take 4.6 seconds to get to 99% of your maximum value, or within 1% of your maximum value. And then for the last one, you want to get to 0.1% of your maximum value. So that's negative t, or rather negative tau, times the natural log of 0.0010. So the smaller the number, assuming you're less than 1, the bigger the, at least in the negative direction, your natural log becomes. And so you get 6.9 times tau. So it takes nearly 7 time constants to get within 0.1% of your maximum value. But keep in mind that L is generally less than 1, unless you inserted a piece of iron inside. But L is generally less than 1. The resistance tends to be greater than 1. So your time constants are usually a small fraction of a second. So it's under fairly rare circumstances that you can observe in real time the building up of current in an RL circuit. And usually you need an oscilloscope or some sort of assistance that works on very small time scales in order to see the voltage building up, or the current building up over a very small period of time. Okay, so that's all for chapter 30 that we're going to cover, and that's everything that we're covering in this course. So the next lecture that I'm going to put up is a review for the last exam, which will take place on Tuesday the 21st, I believe. And, that's the last day of the course. And so if you have any questions, as always, do not hesitate to email me. Otherwise, good luck with everything, and I will talk to you soon.